Hi, welcome back to Geometry. This is sections 5.2 through 5.4. We're actually going to discuss 3 sections today. These are all about special segments that are included in triangles and their relationships. So we're going to explore them all through these notes, and then we're going to do an activity in class. So our objectives here are to use properties of perpendicular bisectors and angle bisectors. We're going to identify properties of perpendicular bisectors and angle bisectors, and then we're going to identify properties of medians and altitudes of triangles. So we'll begin with section 5.2, perpendicular bisectors and angle bisectors. It's essential to your understanding that you know there is a special relationship between the point on the perpendicular bisector of a segment and the endpoints of the segment. So let's begin with Theorem 5.2, the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant, that means equal distance, from the endpoints of the segment. So if this line PM intersects segment AB and it's perpendicular and it bisects. So line PM is the perpendicular bisector of AB, and point P is on the perpendicular bisector. Then you know PA is congruent to PB. So again, this line PM is perpendicular to AB and it bisects. It cuts them into 2 congruent segments where AM is congruent to MB. Then you know that P is equidistant from the endpoints of this segment. So that's the perpendicular bisector theorem. Make sure you take notes in your template. You might remember the word converse. Converse means backwards. So if a point is equidistant from the endpoints of a segment, so in this case, PA is equal to PB, they're congruent, then that must mean that P is on the perpendicular bisector of segment AB. So if a point is equidistant from the endpoint of a segment, then it is on the perpendicular bisector. So because we knew that segment PA was equal to segment PB, PA was equal to PB, that means we know that P is located on the perpendicular bisector. So take notes in your template. So let's use it. It'll make more sense. Using the perpendicular bisector theorem, what is the length of AB? Well, in this picture I can tell that segment BD is the perpendicular bisector of segment AC. Therefore, I know B is equidistant from the endpoints. So that means AB is congruent to BC. So in order to solve for the length of AB, I would set these two equal to each other. So I would say 4x is equal to 6x minus 10. Then we would collect all the x's on one side of this equation to get that negative 2x is equal to negative 10. Then we would use the division property of equality to solve for the value of x. Once we found that x is equal to 5, then we could substitute it in to the expression that represented AB. AB is 4x. So the length of AB would be 4 times the value of x, 4 times 5. So AB would equal 20. And that would mean that BC should equal 20 also. 6 times 5 is 30 minus 10 is 20. Both of these segments are 20. The reason being is that B is located on the perpendicular bisector of this segment, so it's equidistant from the endpoints. So those are equal to each other. And then from here, you would be able to prove that these 2 triangles are congruent, right? We would have hypotenuse leg. Also, you know that this is an isosceles triangle, so we could prove, using our isosceles triangle theorem, that the base angles are congruent. So you could use angle, side, angle, or angle, angle, side to prove that these two triangles are congruent. You try this next one. What's the length of QR? If Q is on the perpendicular bisector of PR, then Q is equidistant from the endpoints. Pause the video. You try. See if you can find the length of QR. When you're ready, unpause the video and check your work. So because Q is on the perpendicular bisector of PR, you know QR is equal to PQ. If we substitute in the expressions, 5n minus 7 is equal to 3n minus 1. Collect all your n's on one side and all your numbers on the other. You would solve for the variable that n is 3. QR is 3n minus 1, so if we substitute in that value, 5 times 3 minus 7 is 8. To make sure you're right, you should plug it into the other because these should be congruent. 3 times 3 is 9, minus 1 is 8. The next theorem that we have is 5.4, the angle bisector theorem. If a point is on the bisector of an angle, then the point is equidistant, and again that means equal distance, from the sides of the angle. So if ray QS bisects angle PQR, bisects means cuts in half, SP is perpendicular to QP, and SR is perpendicular to QR, then you know these segments are congruent. It's important that they're perpendicular. If they're not perpendicular, then you don't know they're congruent. You have to know all of this. You have to know that the ray is the angle bisector, and you have to know that these are right angles, that they're perpendicular. If you don't know that, then you would not be able to tell that these are congruent. So this is the angle bisector theorem. So the point that's on the ray would be equidistant from the sides. So S is equidistant from P and R because it was on the angle bisector and is perpendicular. SP is perpendicular to QP and SR is perpendicular to QR. And then we have the converse of the angle bisector theorem. If a point in the interior, that means inside, of an angle, is equidistant from the sides of the angle, then the point is on the angle bisector. So if we know that S is equidistant from P and R, and again, you have to know the right angles, right? Then you know that it is on the angle bisector. So then you would know that these angles are congruent. So let's use the angle bisector theorem. It's confusing until you use it. So what's the length of RM? Well, we know that NR is the angle bisector of this angle LNQ. We also know that R is perpendicular to this ray, and RP is perpendicular to this ray NQ. So because it's on the angle bisector and these segments are perpendicular, then we have enough to know that these are equidistant. So you would say that you know segment RM is equal to segment RP. If RM is 7x and RP is 2x plus 25, then we can solve for the value of x. So we would know that 5x is equal to 25, and therefore, using the division property of equality, x is equal to 5. We can substitute that value in to find the length of RM. If RM was equal to 7x, then 7 times 5 is going to be 35. Rm equals 35. And we could substitute the value of x in to Rp to make sure that we're correct. 2 times 5 is 10 plus 25, so Rp is also 35. Both of these segments measure 35 units. What's the length of FB? You try this next one. Pause the video, make sure you're correct. You know that F is on the angle bisector of this angle BCD. FB is perpendicular to this side of the angle, ray CB, and FD is perpendicular to this side of the angle, ray CD. So therefore, using the angle bisector theorem, you know that these two segments are congruent. Solve for the value of x and find the length of FB. Pause the video, check your work when you're done. So if F is on the angle bisector of angle BCD, then FB is perpendicular to ray CB and FD is perpendicular to ray CD, then these segments are congruent, and if they're congruent, they equal each other. So you would set the expressions equal to each other, collect all of your variables on one side and all of your numbers on the other. Using the division property of equality, you would solve for the value of x is 3. And once you find the value of x is 3, you would substitute it in to the expression that represented segment FB. FB was equal to 6x plus 3, so 6 times 3 is 18, plus 3 is 21. To double check and make sure you're correct, 4 times 3 is 12, plus 9 would be 21. So the length of FB is 21 units. On to section 5.3, bisectors of a triangle. It's essential that you understand for any triangle, certain sets of lines are always concurrent. Concurrent's an important vocab word in this section. Two of these sets of lines are the perpendicular bisectors of the triangle's 3 sides and the bisectors of the triangle's 3 angles. A perpendicular bisector, we just discussed in the last section, of a triangle is a line, array, or a segment that is perpendicular to the side of a triangle at the midpoint of the side. We've already learned about midsegments. When 3 or more lines or rays or segment intersect at the same point, then they are called concurrent. Concurrent means they all meet together. The point of intersection of concurrent lines is called the point of concurrency. It means where they all meet up. The point of concurrency of the perpendicular bisectors of a triangle is called the circumcenter. All of these special lines and triangles, they all have their own special point that they meet at. It has its own name. It's not essential that you memorize these names, but it's important that you understand what a perpendicular bisector is and what an angle bisector is. Angle bisectors of a triangle, they bisect angles of a triangle. Their point of concurrency is known as the incenter. So angle bisectors are at the incenter, perpendicular bisectors are at the circumcenter. So this is the theorem 5.6, concurrency of perpendicular bisectors theorem. This is the important part, the mathematical part that we're going to discuss. The perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. So, XP, YP, and ZP are all perpendicular bisectors of this triangle ABC. They're perpendicular to the side and they cut the side in half. They are all equidistant from the angles. So the perpendicular bisectors are all equidistant from the vertices. So this segment PA is equal to this segment PC, which is equal to this segment PB. You might remember that we just discussed these when there was just one. Now there's 3 together, right? P is on the perpendicular bisector of AB, so it's equidistant from A and B. P is on the perpendicular bisector of BC, so it's equidistant from B and C. P is on the perpendicular bisector of AC, so it's equidistant from A and C. The circumcenter of a triangle can be inside, on, or outside the triangle. This isn't in your notes, but just so you are aware, it doesn't have to necessarily be in the center. It's not in the center, necessarily. If it was an equilateral triangle, then it would be in the center, but otherwise, it's not in the center, the perpendicular bisector, but it still means that these would be equidistant from the ends. Concurrency of angle bisectors. The bisectors of the angles of a triangle are concurrent at a point, equidistant from the sides of the triangle. So the angle bisector theorem, they kind of seem backwards, the perpendicular bisector theorem and the angle bisector theorem. The angle bisector theorem, these are the segments that go to the sides that are congruent. So we just discussed how when a point is on the angle bisector, then it's equidistant from the sides if it's perpendicular. So that's how we can prove this one. This is three angles put together. That's what a triangle is, right? So the short sides, these little segments that are perpendicular, they are the ones that are congruent. They're not bisectors. They're not perpendicular bisectors. You can tell, right? This is not congruent to that. That's not true. It's these little lines inside that are congruent. Let's use these theorems. So the perpendicular bisectors of triangle HIJ meet at K. So remember, we said that if it's a perpendicular bisector, then they are concurrent at a point that's called the circumcenter. So K is the circumcenter of this triangle. It's where all of the perpendicular bisectors meet. So KL is a perpendicular bisector, KN is a perpendicular bisector, KM is a perpendicular bisector. This means, then, that all of the segments that go to the angles are congruent, right? K is equidistant from the ends here. K is equidistant from the ends. So those are all congruent. If I to J is equal to 18, and K to J is equal to 12, let's find these other segment lengths. So if KJ equals 12, that's this one here, what would HK be? Well, HK would also be 12. All of these would be 12. And if IJ, that's the side, right, this whole thing here is 18, then what would IM be? Well, because KM is the perpendicular bisector, it cuts it into two congruent segments. So these would each be 9. So IM would be 9. Let's try some more. So R is the circumcenter. So circumcenter, that means that these are perpendicular bisectors. Perpendicular bisector. Perpendicular bisector. Perpendicular bisector. Therefore, you know R is equidistant from the end points of each of these segments. So if OS is 10, so let's label our picture here. If OS is 10 and QR is 12 and PQ is 22, this whole thing out here is 22. Let's find some measures. Well, OP, what would O to P be? If half of it is 10, then the whole thing would be 2 10s, it would be 20. RP, well, RP would be equidistant. So if RQ is 12, RP would also be 12. OR, what would that be? Again, it would be equidistant from the endpoints, so it would be 12. And then lastly, TP. If we know this entire side is 22, then TP would be 11. Remember to write down any questions that you might have. You can ask tomorrow in class. Now let's try some with angle bisectors. The angle bisectors meet at the incenter. And if it's an angle bisector, then that means that it cuts these angles into two congruent angles. And therefore, all of these segments would be congruent. So, they all meet at point D. Find DE. Well, if DF is 17, DG and DE would also be 17. It's really that easy. DC is 28. DC is not congruent to these segments. Again, let's use this idea of angle bisectors. Angle bisectors, if we know it's an angle bisector, then we know all of these segments that are perpendicular to the sides are congruent. So if PR is 3 and PC is 5, what's PQ? Or QP? All these blue ones are going to be congruent to each other. So if PR was 3, QP will be 3. All right, let's talk about medians and altitudes. It's essential for you to understand a triangle's medians are always concurrent. They always come together. A median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. The point of concurrency of three medians is called the centroid of the triangle. An altitude means how tall something is, of a triangle, that can happen outside. You've seen examples of that, and we'll explore that more in class. But an altitude of a triangle is the perpendicular segment from the vertex of the opposite side to the line that contains the opposite side. So much easier for us to just look at some examples of that, right? The lines containing the three altitudes are concurrent and meet at a point called the orthocenter of the triangle. The orthocenter doesn't have to always be on the inside of the triangle either. Let's take a look. Concurrency of medians theorem. The medians of a triangle concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So, the medians. The medians go to the midpoint of the opposite side. So it's 2/3 and 1/3. So if you have the measure of the entire segment, DJ, if you knew that it was 9, for instance, then you would know that D to C is 2/3 of 9, so it would be 6, and C to J would be 1/3 of 9, which is 3. Concurrency of altitudes theorem. The lines that contain the altitudes of a triangle are concurrent. That's the only theorem that you have. That's the only rule there is about altitudes. Altitude is just how tall a triangle is. It's the straight segment, so it's perpendicular. You've seen examples of this before. Let's try some of this. So using the medians of a triangle, if D is the centroid, that's how you would know that these are medians, because they're the centroid. And D to G is 4. So D to G, that's the 1/3. That's the small part that goes from the centroid to the side. That's the 1/3. That means D to B would be 2/3. So let's find the whole thing. If D to G is 4, and that's 1/3, then we would say 3 times 4 to get the whole segment. 3 times 4, because remember this is thirds, and 1/3 is 4, so we would multiply it times 3 to say we know BG is 12. BD would be 2/3. So it's twice as big as this segment. If this is 1/3, then 2/3 is 2 times that. So BD would be 8. 2/3, 1/3. Let's use this figure in the given information. If D is the centroid, so again, centroid tells you it's the median, so we're going to read the whole 2/3, 1/3 thing. BE is perpendicular to AC. AB is congruent to CB. FB is 5. EC is 3. DF is 2. How would we find CF? So remember, this is the median. So it's split into 1/3 and 2/3. The 2/3 side is always the one that goes to the angle. The 1/3 is the segment that goes to the side. So CF would be this whole segment. If 1/3 of it is 2, then the whole thing would be 6. Because I'd multiply it times 3. What is C to G? C to G. How would I find that? Well, AB is congruent. These are medians. So that means that's the midpoint. So if this is 5, this is 5. Remember, AB was congruent to CB. So that means this whole side is 10. These are medians, so they meet at the midpoints. So that means that this would be 5 and this would be 5. So CG is 5. Medians are the lines that go to the midpoints of the sides of the triangle. It doesn't cut the angles in half. It goes to the midpoints of the sides. What would CD be? Well, if we know FD is 2, and that's 1/3, then CD would be 2/3, so it's 2 times FD, so CD would be 4. Find the perimeter of triangle ABC. Well, we already said these are medians, so that would be 5, that would be 5, that would be 5, that would be 5. So this whole side is 10, this whole side is 10. Median, so if this is 3, this is 3, so this side is 6. Perimeter is when you add up all the side lengths. So 10 plus 10 plus 6, the perimeter of triangle ABC would be 26 units. So that's the end of tonight's notes. We're going to put all these into action. I'm going to give you a summary sheet tomorrow in class. You don't need to memorize all of these things. You need to be able to refer to them, though. The major concepts that we went over were medians, perpendicular bisectors, and angle bisectors. Please make sure you ask any questions tomorrow in class.